All right. Hello, we're Amy and Ethan, and our project was getting robots to rock climb in space. In a zero-gravity environment, a manipulator's center of mass will remain stationary unless it somehow interacts with external objects. Our goal is to achieve controlled motion of a free-floating manipulator's center of mass within this environment. The challenges we addressed are 1. Finding graphs robust to applied forces in certain directions, and 2. Controlling a free-floating manipulator.
Our grasp planning approach, like many others, has 2 key components. First, we sample grasps. We do this in 2 ways. On the top left, we sample certain endpoints of an approach vector from spheres around the rock hold. On the top right, we leverage the fact that our gripper is a hook and sample approach vectors from a probability map with density around the rock hold's edges, where a good grasp is likely. We also align our vectors with the direction of force we care about. After we sample the approach vector, we set an orientation that aligns the gripper with this vector, and then perturb this orientation with a sampled quaternion from a Bingham distribution. We accept a grasp candidate if it introduces contact between the rock hold and hook of the gripper while following the approach vector. The other major component of our grasp planning is scoring grasps. To do this, we apply forces in directions we care about to the candidate grasps and observe how this displaces them. We then assign a weighted score based on these displacements. Here are examples of grasps generated with this approach. For these grasps, we care about being able to exert a force downward with respect to the slide. The histogram of grasp poses on the left shows 3 peaks, here with low, medium, and high scores in green, yellow, and red respectively. Low scores indicate resilience to perturbing forces applied to the grasp. On the right, we can see that the effects of applying these forces to grasps from these 3 categories. Generally, we see that the lower the grasp score, the more stable the grasp is. Note the pooling of grippers inside the hold in the medium category. These types of grasps make up the majority of this category. One issue we observed was that this selected metric does a poor job weeding out grasps that slip but are caught by something else. Grasp planning concludes by sending the best gripper pose and approach vector to the motion planner.
Once we have the grasp pose and approach vector, we first compute a pre-grasp pose which aims to offset the end effector from the grasp pose. Doing this helps us to avoid accidental collisions with the hold while in transit. The next step is to move the arm to the pre-grasp pose. We accomplish this by using a pseudo-inverse and inverse dynamics controller where the Cartesian, angular, and linear velocity components are computed based on the base's current position to compensate for its drift. The final step is to pull on the hold by using a hybrid Cartesian and force controller. This controller attempts to maintain the orientation, x and y positions of the gripper while exerting a fixed amount of force along the negative z direction in the frame that's defined by the grasp pose. Using the grasp frame instead of the world frame enables the robot to climb holds in a variety of orientations. While our approach is capable of executing grasps in some rock hold positions, it runs into issues with dynamic singularities since its workspace is not only dependent on geometry, but also its mass and inertia. Characterizing the reachable workspace would allow us to only consider grasps that can be successfully executed. Another issue with our approach is that pulling down is not always the optimal strategy for movement. When rock climbing, it is often advantageous to push on the hold to pivot your center of mass upwards, which our system currently doesn't do. Thanks for listening.